Okay, so I'm going to be doing a very brief introduction to an oscilloscope here. Um, since this is COVID times, you will be doing your experiments virtually using software with a virtual oscilloscope, but it's important that you understand what an oscilloscope is, what it does, and how it works, so that your experiment is a meaningful one. Your virtual experiment is meaningful. Okay, so this is an oscilloscope. Okay, an oscilloscope is a measuring device. It measures signals. Okay, it measures signals that change in time very quickly. So what you're seeing right now on the screen is you're seeing two signals. This signal and this signal, which are input from a circuit that I'll show you in a second. Okay, so the idea is, right, that this device, through an input, okay, takes in a signal that is changing in time on a very fast scale. The x-axis on this screen is time, and right now this represents a few milliseconds in time. And this axis, the y-axis, is voltage. Okay, so you are looking at signals that are changing on a very fast time scale, on a time scale of milliseconds, right? Going, in this case, you have a capacitor that's charging and discharging, and you have a battery that's turning on and turning off every millisecond or so. Okay, so how does this device work? So let me look at just one of the signals. So I'm going to just go look at one of the signals individually, and I'm going to turn the other signal off. Okay, and essentially, okay, right now I'm not sweeping in time. So the voltage that's coming in through this second channel on the right here, through this second channel, is a signal that is going up and down. Okay, it's going up and down. As it goes up and down, the beam back here sweeps up and down, and you see a vertical line. Okay, so you can't see how that's changing in time because it's just going up and down, because the signal is just going from 0 to a maximum value, back down to 0, back down to a maximum value, and you just see a vertical line. So in order to see how that dot that's moving up and down is changing in time, what we do is we sweep across the screen at a regular interval. Okay, and as we sweep across, okay, we see how this dot is going up and down in time. Okay, right now it's just going up and down very, very quickly in along this vertical line. So to do that, right, I turn on it, I go to a particular time scale, okay, and you can see that what was going up and down is actually over time, in this case, a charging and discharging with a time scale that depends on, the particular signal you're looking at. Okay, so let me go through all of the controls on this screen. So I'm going to have both signals on right now. So I'm going to have channel 1 and channel 2 both on. Okay, there. Okay, so what do we have here? We have input 1. This is the voltage input that corresponds to the on-off signal, right? This is basically the battery in my circuit with a switch, and that switch is turning on, and then it's turning off, and then it's turning on, and it's turning off very, very quickly. Okay, and this here is my second channel, which is the signal from across what's a capacitor in my circuit, which, as you can see, charges up to a maximum value of the battery voltage, and then discharges back down to 0, and then charges back up to the maximum voltage of the battery. Okay, this region here is the time scale. Okay, so if I change my signal, I'll see a different pattern on here. So let me move over to my function generator. Okay, my function generator, this is my function generator. What I'm doing is I'm generating a square wave. A square wave is basically a battery and a switch. And the switch turns on and off every, at a regular interval. Okay, so right now I have it set to about 88 hertz, 87 hertz, which means that 87 times a second, this switch turns on and off. Okay, so let's look at what happens at this with this pattern as I change the frequency of the switch essentially. Let me turn off the second signal so you can just see the first signal. Okay, that's the on-off switch. Notice that as I increase the frequency, the on-off happens faster and faster. See, I'm changing the signal. As I increase the frequency, you can't really see that. Okay, let me. Okay. As I increase the frequency, so it's turning on and off more times per second, right? As I do that, you see more and more cycles on the screen. As I decrease the frequency, you see fewer and fewer cycles. If I look at both signals at the same time, right, you can see how that second signal behaves as I turn on and off more quickly, so the capacitor doesn't have time to fully charge, and more slowly, so the capacitor actually has a chance to charge and fully discharge. Okay, so what I'm doing there is I'm actually changing the signal itself, the input signal. Now, if I don't change the signal, I can actually zoom in or out of the picture, right? So if I change the time base, this time base tells me how many milliseconds every box, every horizontal box represents on this screen. Okay, so if I increase the time base, so I have more seconds per box, then looking at the same signal, right? The signal is magnified. I'm not changing the signal, I'm just zooming in on the signal, right? As I zoom in on the signal, the range here, right, represents a smaller amount of time. Okay, so it's a smaller amount of time. I'm zooming in. If I decrease the time base, or I increase the time base rather, every box represents a shorter amount of time. So I see more and more. I see more and more cycles because every box is a shorter amount of time. Okay, so that's changing the rate at which I'm sweeping across, right? So it's changing the magnification with which I look at a signal that is not changing, okay? So that's the time base. When I'm using this time base, I read how many milliseconds or microseconds per box I have, and I can then count the boxes on here between two events and figure out how much time it took to get from here to here, okay? So I have 1, 2, 3 boxes from here to here, or 6 boxes, 1, 2, 3, 4, 5, 6 boxes from here to here. So one cycle is 6 boxes, and in this case, one box is 2 milliseconds. So 2 milliseconds times 6, right? That's 12 milliseconds. So I have a 12 millisecond period from here to there based on this time base. Okay, I always want to make sure that I have this fully calibrated, because if this is not clicked into place, then these numbers do not correspond to the actual rate of sweep of this oscilloscope. Okay, so I can move my signal around back and forth using the position knob, and I can zoom in or out of the signal by changing the time base, by changing the amount of time per horizontal box, per horizontal division on the screen. Okay, that's my time base. That's the x-axis or the t-axis, right? The horizontal axis. Okay, then I have my vertical axes, right? These are my actual signals. So I can move them up or down, right? This is my first channel, channel 1. That's this channel. I can move it up or down using this position knob. This is my second channel, my second signal. I can move that up and down like this, okay, to position it so I can make measurements. And I can change the scale, okay? So again, I'm not changing the signal itself. The signal is whatever voltage it is, okay? But I have here my volts per division horizontally set to, right now, 5 volts per division, okay? So 5 volts per division means that each box vertically represents 5 volts. If I turn this, each box now is equal to 2 volts. Here it's 1 volt, and I can change, that's the wrong one, hang on a second, yeah. Let me get rid of the second, let me, hang on a second, okay. So, let me look at just one signal at a time, okay? Oh, it's getting very big there, you see? That my signal is off the screen now. So what I'm going to actually do is I'm going to change the actual size of the signal by changing the amplitude of the signal itself so I can show you what's going on here. Okay, so I'm going to actually change the amplitude of the actual signal on my battery, on my function generator, okay? So it's actually somewhat smaller, okay? So there I have a smaller amplitude of my signal. Then if I change my scale, right, I'm just zooming in on the signal, okay? If I look at both signals together, so I'm going to look at both signals together, okay? As I change this scale, I change the scale of my square wave, and if I change this scale, I change the scale of my capacitor, okay? So by changing this knob, by turning this knob, I can read the number of volts per division. Right now it's set to 5 volts per division. Here it's set to 1 volt per division. Here it's set to 0.2 volts per 2 volts per division. And here it's set to 5 volts per division. So 5 volts per division, 2 volts per division, 1 volt per division, half a volt per division, and there I have 0.2 volts per division. So I'm zooming in as I turn that, right? And I can do the same thing with this scale for the square wave, right? So right now it's on 1 volt per division. So each vertical box represents 1 volt, okay? Here, each one represents 2 volts. Each box represents 5 volts. And then going back up again, 2 volts per box, 1 volt per box, half a volt per box. You can see the same signal is expanded because you're zooming in on the signal. Okay, so I'm going to set this back to 1 volt per division here and 1 volt per division on here. So basically, right now from this point to this point, I have, if I move these, if I align these with the boxes so I can see exactly where they are, I'm reading here 1 box, 2 box, 3.5 boxes. 3.5 boxes vertically is 3.5 volts. So this distance here vertically is 3.5 volts right now. Okay. Here I have this controls what I look at. So I can look at just channel 1 by setting this to channel 1 here. Now I'm looking only at the signal coming in here, which is the square wave, which is the battery with the switch. Okay, I can look just at the second signal, which is the capacitor that's charging and discharging, or I can look at them both together. I can put it on dual and I can see them both together at the same time. Okay, and I can turn off just one of the signals by setting this knob here or this lever here to ground. That basically turns off that input. Okay, and I can do the same thing here, turn off this input. Okay, you see that the square wave just becomes a straight line because it's at 0 now. Okay? All right. The final thing on this oscilloscope that you need to understand is this segment here. This is the triggering. The triggering basically tells the oscilloscope when to start the time sweep. Okay? So when to go back and re-sweep so that you get a stable signal. Okay? So you want to set the source, you want to trigger on a particular signal. Right now I'm triggering on channel 1. And I've set the triggering mode to auto, just always keep that at auto. Okay, so what this does is it basically looks for the first signal to reach a particular level, right? So it looks for this signal to reach a particular level. Every time that voltage reaches that value, the sweep goes back to the beginning. so that basically you are synchronizing the up and down motion with the left and right motion. And if I change where that happens, notice that things start to drift, because in this case, right, I'm restarting my time sweep, my vertical sweep at a different rate than my signal up and down is changing, so the signal scrolls down. So I can change the level, look for a particular time at which you reach a particular value and restart my sweep and find a stable signal. If I'm too far one way or the other, right, if I never reach the value where it doesn't know when to start its resweep, and I start scrolling. Okay, so I want to set my level to a place where, you know, I restart my my time sweep, my horizontal sweep to match exactly a particular point on the vertical voltage of channel 1. Okay, I can look at channel 1 or channel 2, or I can look at the line, which is basically just the power coming from the wall, to look for a particular value of voltage that tells the oscilloscope now it's time for me to resweep back to the beginning. Okay, to resweep back to the beginning. Okay, I can source on channel 2. If I source on channel 2, I change the level. See if I, depending on what value of voltage I look for in channel 2, I don't get a stable signal. Okay, so I can trigger to get a stable signal. Okay, so that's how the oscilloscope works. Let me show you precisely what the circuit is that I'm looking at here. Here's the circuit I'm looking at. Okay, so the circuit I'm looking at is here. Let me remove my probes. My probes are how I make measurements with the oscilloscope, okay? My channels. What I have here is I have my battery, right? My battery. I have the high voltage side going to a resistor. It's going through the resistor. The resistor is in series with a capacitor, and then back through the black line back to my voltage source. My voltage source is a battery with a switch that's turning on and off right now 88 or 89 times a second. Okay, because I'm on basically 88.7 hertz, which means 88 times a second, this switch is turning on and off. So my channel 1, this is my channel 1. This is my channel 1 probe. And notice, by the way, that I've set this to 1x. This is a special probe that ensures that the oscilloscope doesn't become part of the circuit. It stays basically isolated from the circuit. There's capacitance and resistance in here that make sure that's the case. Okay, I'm using channel 1, which is connected to this input. Okay, channel 1. I'm connecting to my battery. Okay, this is where my battery is. This is the ground side. This here is the ground side, this little clip. So in principle, the clip should go here to the ground. Okay, but it doesn't really matter in this case because there's an internal ground in the oscilloscope. Okay, so I'm basically looking at the voltage here with probe 1, and you can see there it is, right? There's voltage 1. There's the input voltage, the battery. My second probe, here's my second probe, which is connected. This probe is connected to channel 2, and my second probe, I'm using it to look across this capacitor. So here's the ground, the bottom of the capacitor. Here's the top of the capacitor. If I connect it here, I'm looking at the voltage between the top and bottom of the capacitor, same ground as the battery. And if I put that on there, notice I see now my capacitor voltage at the same time as I see my my input battery voltage with the switch. Okay, let me briefly show you how we measure frequencies. Okay, so let me set my frequency to something simple like 100 hertz. Okay, so I'm going to change my frequency now to 100 hertz. Okay, so that's set to 100 hertz. That means the switch is turning on and off 100 times every second. Okay, 100 times every second. Okay, 100.100, close enough. Okay, now I want to verify that I'm actually measuring that rate, that frequency. So the way I'm going to do it is I can't measure frequency directly, but I can measure period. And period is 1 over the frequency. The period is the time it takes for the signal to repeat. So let me position this. I'll start here, okay? So I'll position my signal there, okay? And let me change my time base. Let me change my time base to expand this a little bit, okay? So now I'm expanding my time base, all right? So how many boxes for one period? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 10 boxes horizontally. 10 boxes horizontally. I look at my time base, and I see that my time base is 1 millisecond per box. So 1 millisecond per box, 1 millisecond times 10, that means this whole time from here to here is 10 milliseconds. 10 milliseconds, that's 10 times 10 to the minus 3. So that's 10 to the minus 2, 10 to the minus 2 seconds. So this is all 10 to the minus 2 seconds. 1 over 10 to the minus 2 seconds is 10 to the 2, which is 100, which is, of course, 100 hertz. Okay, so my input signal has 100 hertz. 100 hertz corresponds to a 10 millisecond period. So I've measured the period of the signal that I set here at 100 hertz. I measured the period of the signal at 10 milliseconds, 10 millisecond period, 1 over 10 milliseconds, that's 100 hertz. So that worked. Okay, I can, let me look at just the input signal. Let me turn off the capacitor. I can look at all kinds of signals. I can, instead of generating a square wave, I can generate a triangle wave. I can generate a sine wave, right? There's a sine wave, right? And I can measure the frequency of my sine wave in the same way, right? By counting the number of boxes for one period, right? And that, again, will give me 100 hertz because I haven't changed it. If I change the frequency, here I'm changing the signal, right? If I increase the frequency, now I've set it to about 200, right? 200 hertz. At 200 hertz, my period is half of what it was before because I'm going through 200 cycles per second instead of 100 cycles per second. Okay, so that is basically what an oscilloscope is. It's a measurement device that measures voltages, signals that are changing very quickly in time. Okay, the voltage is along the y-axis, and the time is along the x-axis, and the scale for the time is set by the time base. The scale for the voltage is set by the voltage base here, the voltage per division here for channel 1 and here for channel 2. Okay, and so you probe voltages, you measure voltages by taking your probe and setting it in a particular, looking at a particular location on a circuit. One last thing I'm going to show you before I stop. I'm going to set this to just channel 1. There's my channel 1 right now. It's a sine wave. I'm going to remove my probe from my circuit. Okay. I'm going to remove my probe from my circuit. And I'm going to look at what's a built-in calibration. You can't read this probably, but what this says here, it says 2 volts peak to peak, 1 kilohertz. This is a calibration signal. If I put this here, I should be seeing a 2 volt peak to peak, 1 kilohertz signal. Okay, that's what I'm supposed to be seeing here. It's hard to measure that because my scale is so big. Okay, so in order to actually measure it, what I'm going to do is I'm going to move my signal to a convenient place, like so. Okay, like there. And I'm going to change my time base. And notice how I have between this point and this point 2 boxes. That's 2 boxes from here to here. And my time base is 1 volt per box. So this vertical distance is 2 volts. Well, my calibration says 2 volts peak to peak, 2 volts. That matches. Okay. My frequency, it says it's 1 kilohertz. What is so to measure my frequency to see if I'm properly calibrated, let me increase the time scale here. Okay. So I'm right now at 0.1 milliseconds. So 0.1 milliseconds per box. 1 box, 2 boxes, 3 boxes, 4, 5, 6, 7, 8, 9, 10. 10 boxes. 10 boxes, each box is 0.1 milliseconds. Okay, so this total distance from here to here, 10 boxes is 10 times 0.1 milliseconds, which is 1 millisecond. So right now I'm looking at a 1 millisecond, or 10 to the minus 3 second time between this and this. 10 to the minus 3 seconds, 1 over 10 to the minus 3 seconds is 10 to the plus 3 hertz. 10 to the plus 3, that's 1 kilohertz. That's what the calibration says. Okay, 10 to the 1 kilohertz, 10 to the 3 hertz. So I'm measuring a 1 kilohertz signal here. If I change my time base, I see more cycles. Okay, but I'm still seeing a 10 kilohertz signal, 10 kilohertz from here to there. I'm sorry, 1 millisecond from here to here for every period. And my peak-to-peak voltage, 2 boxes, 2 volts, which is what my calibration says. Okay, so that's basically what an oscilloscope does. You will be making measurements with a virtual oscilloscope using virtual circuits in the following several labs for the semester. Okay, that's it.